projector turned on. We are now recording. Let's go to our current slide. And that's where we'll be beginning, but we do have a few announcements first. Now, first, I assume at least a few of you may go to the Birmingham campus as well, right? You may be already aware of this, but if you're not, you need to be. From what they said in an email that I received yesterday, hopefully it wasn't April Fool's, Monday, the Leon Kennedy Student Center is closed, okay? So I know the cafeteria, food service has been moved to the new Academic Success Center. It's a little bit further away, but brand new building. As far as I know, the bookstore is also moved. As far as I know, the Space Center, I believe, certainly has moved. Lots of things. So many of the offices and things like this, student services, have moved to the new building. I assume that even the police department moved to the new building. If they closed Leon Kennedy, they had to go somewhere, so I assume they are there as well. So if you're on the Birmingham campus, don't go to Leon Kennedy anymore. Anything you were doing there, go to the new Academic Success Center. Okay. Today, Jake is here. Okay. If you haven't noticed already, it's L Day, and you'll probably be hearing this pretty soon because I bet you they're beginning to fire up some music soon. Don't know if we'll hear it from here, but I wouldn't be surprised if you would. But starts today on this campus at 10 and goes till 1, is my understanding. On the Birmingham campus, it starts at 12 and goes to 3. So you can partake here and then head over to Birmingham campus and partake there as well. They have food, they have music, they have games, they have lots of activity. I don't know how many of these are happening on this campus, but I know that there's quite a few on the Birmingham campus. I know they'll have food and music here. I saw people, or they always do, okay? I see that Jake wore his Lawson material, so he's right into L Day. All right, okay. So that's happening today. This is the administrative calendar. I think I mentioned it last time. A lot of the stuff on here I don't even care about. You probably wouldn't either, but there are a few things that will be coming up, and I'll try to mention those as they get here. I was reminded of something because they came out with an email way back, I think in January or something, and I think it was 40, and I just tried to forget about it, and I was reminded this morning. It's kind of a bad news situation. Next Wednesday, our wonderful administration at the two-year college system has requested the faculty to go to Montgomery, okay? So next Wednesday, 1 week from today, I will not be here, so we will not have class that day. Now, if you have other classes and they're taught by adjuncts, those classes will be meeting. It's only full-time faculty that have to go to Montgomery. So if you're in a class being taught by an adjunct instructor, then go to that class, okay? But if you're in a class like this that's taught by a full-time instructor, check with the instructor to make sure they have to go too, but I believe all of us do have to go. So that's next Wednesday. That's not on this calendar either, okay? Next Thursday, 1 week from tomorrow, is Honors and Awards Day. Now that won't affect this class any, but if you do have a morning class, your 8:30 class may meet. It may be shortened. Check with your instructor. If it's an adjunct, you'll probably meet, okay? If it's a full-time instructor, you may only meet part of the time because the Honors and Awards, I think, starts at 10, doesn't it? Now, you probably have to be there sooner, don't you? 9:30. Okay. So and that's probably the time we have to be there too. So I would be able to meet with my 8:30 class for at least half an hour, but that's about all, okay? Now, some full-time instructors may not even do that. If you're over on the Birmingham campus, they can meet for longer because that's where the meeting is. I have to allow 30 minutes to get there. So check with your instructor. But if you've got a 10 o'clock class, almost certainly that one will be canceled. Now, again, if you've got an adjunct, it may not be. So check with your instructor. What's the next class? 11:30 classes. They may be canceled or they may start late. So check with your instructor. That's next Thursday. Doesn't affect this class any, but your Tuesday, Thursday classes it could affect. All right, so that's the stuff coming up from there. Now, this is something I think I announced to you before about NCAS, the NASA Community College Aerospace Scholars Program. Check it out, folks. It sounds like I have a student in one of my other calculus classes that has participated in it. He gave it very high marks, okay? Really a great opportunity, okay? And I think that's most of what we need here, okay? What else do we have later today? Okay, any questions before we get started today? Sorry to take time at the beginning, but those are pretty important things coming up. All right, I've marked all 1, 2, 3, 4, 5 of you here. So let's get going. Any questions, calculus-wise or otherwise? Okay. We're on in Chapter 4, which is integration. 4.2 is area, and we just started this last time. We're talking here about area of a plane region. That means a region in a plane, okay? That's basically what we'll be dealing with, I think, throughout this section, okay? They don't say much, they just jump right into the problem. Now, here we have a function. F of x is equal to minus x squared plus 5, okay? There's the graph of it, okay? It says, use the 5 rectangles in these two figures to find 2 approximations to the area of the region lying between the graph of f of x equal minus x squared plus 5 and the x-axis between x equals 0 and x equal 2, x equal 2. Okay, now what they've done here is, so far you don't know how to do this. Some of you don't anyway, okay? They're assuming you don't know how to do it. Okay, so what we're doing, we're going 0 to 2 on x, and they're using 5 intervals here. So therefore, the length that they're doing is 0 to 2. 2 minus 0 is 2, divided by 5, so each one of these increments is 2/5. Okay? So that's the thickness of the interval. What they're doing the inscribed rectangles that are under the curve that miss by that amount. Okay, they underestimate the area by that amount, but it's still not a bad estimate. So what they're saying is use the 5 rectangles in here. Over here we're using the circumscribed rectangles, the rectangles that are on the upper part of that. Now, that happens to be this way. What they call this is the right-hand rectangle and the left-hand rectangle. In other words, you're using the right rectangle to intersect here, 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 and here, and you're using the left-hand edge of the rectangle to intersect in those. So that's the difference in these. Those overestimate, these underestimate. So all we're doing, or what's required to do here, if I can find my pen, there it is underneath, okay. We need to find the function values at these points, okay, at 2/5, 4/5, 6/5, 8/5, and 10/5. Over here, we'll also need at 0, okay? And so let's find those values. F of 2/5. Well, that would be, and frankly to me, it's a bit easier to use decimals than fractions, I think, but you can use whatever you want to. This would be 2/5 is 0.4. 0.4 squared would be 0.16 minus 0.16 plus 5 is going to be 4.84, right? Y'all with me? Help me with the calculator, because the old gray cells, I don't like to go this fast, okay? So this is 4.84. That looks about right. That's this value, okay? This one will be at 0.8. So f of, and I'm going to put 0.8, that's easier for me to deal with, is minus, well, 0.8 squared is 0.64, so it's minus 0.64 plus 5, which would be 4.36. And that looks about right too. So that would be that one. This one will be 1.2. I think I can still do that one in my head easier than if I did fractions, but let's try it. The f of 1.2 would be negative 1.44, right? Plus 5, and that would be 3.56. And that looks about right too. That's 3.56. This one here, that's 1.6. Yeah, I think I can do that one too. F of 1.6 is going to be 1.6 squared, I believe, is 2.56. Is that right? Okay, 2.56, negative 2.56 plus 5, and that's going to be 2.44. And that looks about right too. And then this one at 2, I think I can do that one. F of 2 is going to be negative 4 plus 5 is equal to 1. And that looks right. Okay? Now, while we're doing that, let's go on and get an f of 0. I think I can handle that one. F of 0 is equal to 5. Everybody agreed with that one? All right. I could do that without the calculator. Okay. Now, that gives all the values we need. Now we need the area of the rectangle. Well, the rectangle is every rectangle is 0.4, right? The width is 0.4. So 0.4 times this one, plus 0.4 times, or how about, let's just say 0.4 times this, plus that, plus that, plus that, okay? That should give it to us, okay? So 0.4 times, and if you'll add these up, someone ready to do so? 4.84, if I can read my writing, plus 4.36, that's about 9.2, plus 3.56, that's, well, you use the calculator, plus 2.44, plus 1. Has anyone been plugging? Good. 4.84 plus 4.36 plus 3.56 plus 2.44 plus 1. Add those together, see what you get. Anybody? $4.84 plus 4.36 plus 3.56 plus 2.44 plus 1. A little louder? 16.2. Okay. I heard a 6, I thought. My hearing's so bad. 16. Oh, 16. Point what? 0.2. 0.2. Okay. And multiply that by 0.4. And what do you get? 6.48. 6.48. Okay. That's our underestimate of the area under that curve. We know it's an underestimate looking at the graph. Okay? Same deal, Okay? Add 4 to that. Okay, because these numbers are all, not to this answer, but the 16.2. The 16.2 you gave me was the sum of these. Because this has a 5 rather than a 1. But all the rest of the values are the same. So just add 4 to 16.1, that'd be, 16.2, that'd be 20.2. I'm really lazy. Okay? Is that okay to be lazy? See what we're doing? Okay. So you're just adding this difference here. The difference between this one and that one is basically 4. All the rest of them, the values that we're doing are the same. Okay? Because no, yeah, they are. Yeah, because this value is exactly that one. You see, this one's exactly that one. This one's exactly that one, and this one's exactly that one. We're just subtracting the 1 times this and adding the 5, so you're doing 4. So 20.2 times 0.4. Someone do that for me. 0.4 times 20.2. I hope I'm doing this right. And that looks like to me to be 8.08. Okay. 8.08. All right. So we know it's something in between those. Now, they never tell you to do this, but if I were really making an estimate now, I'd add those two together and divide by 2. Okay. They don't ever tell you to do that, but that's what I would do if I was really needing to give a good estimate. And that would be 7.7, maybe? 7.78 or something like that. I don't know. I'm just doing it off the top of my head. Let's see what they get. Hopefully I haven't led you too far astray. 6.48 they got for that one. 8.08 they got for that one, and they don't do the other. We know it's in between those. Okay? I would say take an average and you'll get a little bit closer. Okay? Because you know one overestimates and one underestimates. See what we're doing there? Okay. Not exact. Okay? The right endpoints are the 5 intervals. Intervals of the 5 intervals are 0.25 times I, where I is 1, 2, 3, 4, and 5. And we did those. And we added those together. Okay. And they use fraction forms, and it didn't come out too hard. So that's okay too. Okay. And then they added those together, multiplied them by the 0.4 or 2/5, and they got 6.48. Good for them. Okay. I think decimals was a little easier than the fraction, but maybe not. Okay. And here is at least one of them.
Yeah, my dad left this morning for a mission trip. So
oh, I see. Okay.
I'll be back for a couple of weeks.
Okay. Well, I'll report them as being out of action. You know. Okay. Good deal. Okay. In case you don't go back and listen to the first part of the class, we do not have a class next Wednesday. We have been required to go down to Montgomery, all the full-time faculty, to go to Montgomery for a fun day at the Chancellor's office. So, an enormous waste of time and effort in my mind, but I guess I shouldn't be saying that. Okay. But we're doing the example 3 on page 261. And we've just done this and are confirming that they did the same thing we did. We use decimals, they use fractions. It all works out the same. Okay? And because each of the 5 rectangles lies inside the parabolic region, you can conclude the area underestimates, so it's got to be greater than 6.48. Then when you do on the other side, the left-hand endpoints, those are exactly this. I is 1, 2, 3, 4, and 5. It's 2/5 times I minus 1, because you're using the left-hand endpoint. and that comes up to be 8.08, which is exactly what we got. We did it basically the same way, but we used decimal numbers. And because the parabolic region lies within the union of the 5 rectangular regions that are underestimating and those that are overestimating, you know it's between, I'm sorry, they're just talking about the second group, less than 8.08, okay? So you know the area of the regions in between those. And just to get a little bit better, I would just average the two and tell you, but they're not wanting you to do that now because that's not part of where they're heading, okay? But if you're doing just an estimate, that's what I would do. Okay. Now, they say in the book, by increasing the number of rectangles, you can attain a closer approximation. For instance, if you use 25 rectangles rather than, goodness gracious, 5 rectangles like they did here, you come up 7.1712 and 7.4912, okay? And what was my estimate before? I don't remember. I said about 7.78, I believe is what my guess was. Yeah. And so you see, that was still an overestimate. Why was it an overestimate? Because the errors here are a little bit greater than the errors here. Okay? So that is an overestimate. These two are about the same, and these two are close, but actually that was a little bigger. That's about the same, but this one's, I think that one's the one that pushes a little too far. Okay, so now we got an estimate that looks like it's around 7.3 something. Okay, which would be, I think I was wrong on my estimate before. The average between those, no, my average was 7.18 is what I would have guessed, and I was between those. Okay, never mind. All right. Now, if I had done my math right. Okay. Now, we're going to take that kind of concept and use a limit. And notice there, if you took smaller increments, you got a better estimate. Okay? So that's what we mean by using a limit definition. Let's consider a plane region, that's something on the xy plane, bounded above by the graph of a non-negative continuous function. Here's a non-negative continuous function. Now, we can't include it over here because that goes negative there. As long as you stay anywhere beyond here, okay, it looks like it's going to go positive forever there, but whatever, as long as it stays within here, not over here, but here, then you can do what we're about to do, okay? Non-negative continuous function, y is equal to f of x. We don't know what this one is. The region is bounded below by the x-axis, and left and right by a and b, okay, and on top by the curve, okay? So how are we going to do this? Okay? Now, before, if you recall, that parabola like this, because it was monotonic, the interior ones were going to be undershooting and the exterior ones overshooting. Well, they always are. But in this case, if you're going up this way, your left-hand root is going to undershoot, but the left-hand root will overshoot here. So since you have a change of direction, in fact, 2 changes of direction, you can't say which one's going to win out to be which is going to be greater or less, okay? But you're still going to think through that same kind of issue, okay? So we're going to split this to approximate the area under the region. We'll begin by subdividing the interval A to B into n subintervals, each of which has a width of delta x. What do? B minus A, that's the length this way, divided by n. How many subintervals are you going to do? Last time we did 5, so we did B minus A, 2 minus 0, was 2 divided by 5 is 2/5. Later, they said do 25 intervals, then our 2/25. Okay? That would have been much, much smaller. So here we're going to be generic about it and just have it b minus a over n. Okay? That would be your delta x. Okay? Now they showed some finite amount here, and in this region, that's overshooting. Okay? If you'd have done the same thing here, that one would have been undershooting. Okay? Doesn't matter. That the interval width is delta x. Have y'all run into deltas before? Delta means difference. Final minus initial. Right minus left. Okay? This minus that. Okay? That's what the delta means. B minus A. Okay? Right minus left. Greater minus smaller. Okay? Divided by n, that would be your delta x. That means difference. Okay? Now, the endpoints on the interval is your a, which is your x sub 0. That would be a plus 0 times delta x, because that's where you're starting, a. And then that's going to be less than your x1, which is a plus 1 delta x. You go just one increment further. And then a plus 2 delta x's will be the second increment, and on like this till you get to n delta x's. And if you think about this, delta x is b minus a over n. The n's cancel out. B minus a plus b minus a. A's cancel out, and that's just b. Your x of n would be v. So that works out nicely. Because f is continuous, a continuous function, the extreme value theorem guarantees the existence of a minimum and a maximum value of f of x in each sub-interval. Okay? So we'll call f sub m, I think that's an I, f of m sub I as the minimum value in that ith sub-interval, and f of m, capital M sub I, is the maximum value of f in the ith sub-interval. Okay, that's hard to say sometimes. Let's take a look here. Here, this would be the maximum value, that would be the minimum value. Okay, now if you had a sub-interval that went across a critical point, then neither of the endpoints would be the max, but there would be a max, and one of those is going to be a min. Here, that would be the min, and one of those would be the max, okay? It just depends on where you happen to be. But every subinterval is going to have a minimum and a maximum value. Sometimes, if it's monotonic in that interval, it's going to be at one end, and the other one's going to be at the other end. If it's not, if it's changing direction, all bets are off. But it's going to have a minimum and a maximum value. Okay, so next thing we're going to find a inscribed rectangle lying inside the ith subregion, and a circumscribed rectangle extending outside the ith interval. The height of that inscribed rectangle is going to be your f of m sub I. Whatever that minimum value is, that's going to be your f. The f there is going to be the height of that one, and the maximum, whatever your maximum value is, that would be your f of m, capital M sub I. Okay, so going back here, oops, too far. This value, the f here, would be your maximum, and this would be your minimum. Now, if, like I said, let's just imagine, oh, snuck in on me. Taylor, right? Okay. All right, is anyone else sneak? Ah, Josh snuck in too. Okay. Anybody else? Sneaky people. Okay. And so let's just imagine here if we had done the next delta x here. And this is not a very good rendition. This would be the max, this would be your m, capital M here, and your little m would be this one right here. Okay, this would be the little m. So whatever interval that is, that we'll call it I plus 1. So it doesn't have to be on an endpoint. It can be somewhere in the middle. Okay. Not that that's that important, but just showing you it doesn't have to be on one of the endpoints. It just has to be the maximum and the minimum. Okay. For each I, the area of the inscribed rectangle, inscribed, the smaller one, is less than or equal to the area of the circumscribed rectangle. Okay? So therefore, the area of the inscribed rectangle is L sub m, little m sub I times delta x. And that's less than or equal to, if it was a flat region, L sub capital M. That's the maximum. The x value for the maximum that you have there, delta x. And that's the area of the circumscribed rectangle. Okay. The lower sum of those areas of the inscribed rectangle is called the lower sum, okay, the sum of the areas, and the sum of the areas in the circumscribed rectangles is called the upper sum. So what do they use? Little s for the lower sum and capital S for the higher sum. So this will be the summation of all those minimal rectangles, your minimum height within that delta x, the value there, and this will be the F value at the maximum of those rectangles. Okay? And if you add all those up, this is going to be less than that. Less than or equal to. Okay? Making sense? Now this is introducing all sorts of a lot of text that I've taught from before don't use this max and min, they use left or right. And sometimes they're max, sometimes they're min, sometimes they're neither. As you see, what ultimately we're going to do, hopefully you're already beginning to imagine this, is just let your delta x get smaller, smaller, smaller. So after a while, it doesn't really matter. The delta x's are so small, you're almost the same values. Okay? That's where we're heading. So it really doesn't matter too much. But other calculus texts use left and right rather than max and min. Okay. So here's your sum of all your the minimums. Okay. This is the minimum here. That's the minimum there. Ooh, which one's minimum here? I guess that one is. Okay, it's a little bit less than that. Here's that one's the minimum. That one's the minimum. Here's the minimums right there in the center, as I was showing before. Here it looks like it's the left hand. Okay. Left, left. Okay, so there's just inscribed rectangles. The circumscribed rectangles, you'll take the maximum here. It looks like the maximum's right about there, and then left hand, left, left, right here, and right there. Depends on if you're going up or going down. Okay? The turning points are the hard. But those always overshoot, these always undershoot. Just like when it was monotonic, we just went left and right. Okay. This is not going to give you exact. This is going to be less than. That one's going to be more than. The actual area under there is somewhere in between. Okay? Area of the region is in between those sums. Making sense? Now. Oh no, they're going to have us do this again. Okay. Find the upper and lower sums of the region bounded by the graph f of x equal x squared and the x-axis between x equals 0 and x equals 2. Okay? I don't see them telling us what the interval is. Okay? Did they leave that off? Oh. They're going to keep it generic, okay? So we're not going to get an exact number here, but we'll keep it generic. So your delta x here is what? Anyone remember? The assumption here is, okay, b minus a over n. We're going to assume n subintervals, and that will be b is 2 minus 0 over n, so this is 2 over n. Okay, so there's our delta x. We don't know how many n's we have, but whatever we choose there, that's going to be our delta x. Okay. Now, since this is f of x is equal to x squared, we know what it looks like. This is the parabola going from 2, 4, 0, 0, okay? It's in between those two. So here, however you do this, because this is strictly increasing, your left-hand endpoints are going to be the minimum, and the right-hand endpoints is going to be the maximum, okay? Going back to that concept. It's not changing direction, so you know that's always going to be the case. So, let's do that, okay? Your m sub I, the x value that's on the lower end of that is always going to be when I is going from, let's just, do they call it 1 to n? No, they call it I, okay. So say it's going to be I minus 1 to n, okay? So i's will be going for I minus 1. But that's not quite the best way to say it. You need another increment there, but they don't have it, okay? So, your m sub I will be 0 plus I minus 1 over times 2 times I. So this will, this is not the best way to say that, but I'm trying to think of a better way to say it. Your counter, let me just call it the counter, is going from I minus 1 to n, okay? So that'll be, you're starting at 0, so it'd be 0 plus I minus 1 times your 2 over n, your delta x, okay? Which is, I don't know why they go to the problem of doing this, but they do, 2 times I minus 1 over n, okay? That's the area. That's your little s sub I, okay? Is that, okay? And you sum all those up, okay? And they make this a function of n, which it really is. S is a function of n, is then the summation, using our summation notation, I going from 1 to n. So I had to look and see how they were going to do it. If they were going to do it, I is equal to 0 to n minus 1, then you'd have it one way, but they're doing 1. So since your lower is always on the left, it's going to be I minus 1. So that's why they put that in there. Going from I minus 1 to n of 2 times I minus 1 over n, okay? The 2 over n is your delta x, your I minus 1 is your counter, okay? No, you still got to multiply it, I'm sorry. That's, okay, back up here. Your m sub I is the x value here, okay? And when I is equal to 1, that gives you 0, okay? Because you're adding your delta x to it. So this is that. Then you have to multiply this to get the sum by your 2 over n again. It just seems like you're double dipping here, but you're really not. If you remember back when we did the other one, I hate to go all the way back to do that, but you use your delta x to say how far out you're going, but then you multiply delta x to get the area as well. So the function here is, this is your m sub I, basically this is your m sub I. I said it wrong here. That's what this is, m sub I. Okay, that is what you're entering in your formula here as your x. So you got to take this and square it. Okay, then multiply it by your delta x. Okay, now this is really getting convoluted seeming, but it is okay. Let's actually do that math there. okay, the summation I equal 1 to n of, you got a 2 squared, which is 4 times 2, so that gives you 8. So I just as soon pull the 8 on the outside, okay? Now this gives you I minus 1 squared, which is I squared minus 2I plus 1, okay? And you're over n squared, so let's pull the n squared out here too. That doesn't depend on anything else. So this is your summation that we have to fiddle with, okay? Now, oops, that's n cubed. Sorry about that. Because this was squared, and that's another n there, so it's n cubed. 8 over n cubed times the summation of this. Well, if you think about this, 8 over n cubed times the summation I equal 1 to n of I squared minus 2 times the summation of I equal 1 to n I plus the summation from I equal 1 to n of 1. Okay, that's breaking this summation. When you pulled everything else out, 2 squared times 2, that's your 8, and n squared times n, that's your n cubed. Pull that out. All you have left is this thing squared, okay? And then break this into these pieces, and then you go back to what we did last time, those really fun, get this thing here in terms of n, okay? And let's do that. That's 8 over n cubed times, now, you go back to what we were doing last time. Remember, theorem 4.2, it had your constant, your linear, your squared, and your cube. We don't need the cube. All we need is the squared and down, okay? So this one was boy, my two brackets ran into each other, and that got to be really bizarre looking. N times n plus 1 times 2n plus 1 over 6. Okay? That's that first sum. Minus 2 times, I should have another symbol there, but I'm going to use the same bracket. I was n times n plus 1 over 2. N times n plus 1 over 2. Okay? And then the third one is pretty easy. That's just n. Summation of 1, is 1 plus 1 plus 1 plus 1 n times, so that's just n. They have c times n, but your c here is 1, so that's just n. Okay. Oh, man. See why I love doing them this way. Okay. Let me write it up here. 8 over n cubed times. Okay? Now, just for funsies, you see that every one of these has an n in it, right? There's an n here, an n here, and an n here. Get out of here. Okay, so let's factor that one out, and that leaves this as an n squared. Okay, now let's just deal with the ones we got left. Okay, n plus 1 times 2n plus 1 over 6 minus 2 n plus 2, n minus 2, okay? I just want to multiply that out, plus 1. Okay, that makes it a little simpler, but still messy. And this one was, well, this 2 and that 2 go away, so let's just leave that as n minus 1, okay? And then you have a plus 1, so let's just wipe those out, okay? So what do we have now? This is 8 over n squared, because we factored out the n and took out one of those, times n plus 1 times 2n plus 1 over 6 minus n. Well, let's just make that 6n to put that over 6 as well. Okay? You okay with that? All right. Now we multiply through, goodness, I don't think I need my graph anymore. I hope not anyway. So let me erase the graph here so I can have more room to write. I'll probably regret that one day, but not today. Okay. I think I just lost something, but hopefully it wasn't too bad. Okay. All right. So that's 8 over n squared times, let's multiply through here. That's 2n squared plus 2n plus n, so that's plus 3n plus 1 minus 6n all over 6. So that's 8 over n squared, wish I'd have done something earlier, but we'll do it later. 2n squared minus 3n plus 1 over 6. Now I'm going to do it. This will be a 3, that'll be a 4. Okay? Divide out a 2. So what do we have left? 4/3 times 2, when I bring this inside, minus 3 over n plus 1 over n squared. Okay. Now, I know they don't want us to do this yet, but I'm going to tell you what I'm going to do. I'm going to let n get bigger and bigger and bigger, meaning that goes to 0, that goes to 0, right? So that gives us 8/3. I'm going to guess that answer is 8/3. I hope I'm right. Okay. But they don't want us doing that yet. They want us to just leave it this way. 8/3 minus 4. Ooh. I must have botched something up. Minus 4 over n. Yeah, that's right. Plus 4 over 3n squared. I think I did it right. Okay? Yeah. It's still going to give you 8/3. Okay. If we did the upper one, okay. Yuck. All right. I'm going to leave that result here and erase just about everything else. This is so much fun, isn't it? I probably should have left some of that, but I erased it. I'm getting carried away. All right. I'm going to regret losing all this, but it's just too confusing trying to keep up with it. Let's just do it all from scratch. I think we can lose this too. We just got the result we want. Oh, you're interested in the answer, right? Okay. All right. Now, let's do our m sub I. Okay? Our m sub I will be the right-hand side of this. So that'll be 0 plus whoops. I think I intentionally left that. I want to get rid of it now. 0 plus, let's leave this a little bit longer. Okay. I times 2 over n. Okay? Okay? So this will be, your capital M sub I is 2I over n. Okay? And what we want to do is then f of 2I over n will be 4I squared over n squared, right? Then we'll multiply that by your delta. That's your height. Your width is 2 over n, so you multiply that by 2 over n, and that gives you 8I squared over n cubed. We've seen that before, basically. It'll come back, I think. I hope. Okay? What I've just done, this is this part, then I multiplied it by the delta x here. Okay? So this gives you your s, capital S sub I. Okay? The first sum. So your total s as a function of n is this merely going to be sorry. Let's pull out the things that are constant. S over n cubed times the sum of just I squared. Okay? Makes it much easier to do. And this is why I regret losing 8 over n squared. And the sum of I squared, remember that was the n times n plus 1 times 2n plus 1 over 6. Do I memorize these things? No. I don't think it's worthwhile, especially when you're old like me and you don't have that much memory left. Don't waste any memory on it. You know, look them up if you need them. Okay. Now, what are we going to do with this? Well, this n again will cancel. This is a cubed here. Cancel the cube out this cube and leave you a square. Okay? And then what you have left here is, and the 6 will be a 3 and a 4 here. So what we have left here is 4 over 3n squared times, and then multiply those out. I wish I'd have left that. That's 2n squared plus 3n plus 1. Okay. We already took care of that. Okay. Yeah. Okay. Now, when you multiply that out, what you get is 8 over 3, because the n squareds go out, plus the 3's go out here, and you're left with a 4 over n. And here we have plus 4 over 3n squared. Okay, when you multiply those through, that's what you get. Okay, now how far did that differ from what we had before? Now I wish I'd have written it the way they did. You can factor out a 4/3, and that would leave you with a 2 minus 1 over 3n. I think. I seem to have lost something here, but maybe not. No. 1 over n. You have the 3 out there already. Okay, 1 over n plus no. You have a 3 here. 3 over n. Got it. That's an n. That doesn't look like it. And that's plus 1 over n squared. Okay. So basically, you wind up, I can't believe it. Oh, that's a plus. Sorry. Looks almost the same, only this is a plus or that was a minus. Okay. Well, this one just happened to work there. But in the long run, these don't matter anyway, because if n gets larger and larger and larger, these get closer and closer to 0. So in both cases, you wind up with a limit, which I'm not supposed to say yet, of 8/3, which should be your answer. Okay? Now, boy, is this ever awkward, okay? But it's doable, okay? And you see, okay, yeah. So the way they did it, 8/3 plus 4 over n plus 4 over 3n squared, that's exactly what they got. If I factored it out like I did, then you get this part. Looks very, very similar to the two. Now, that illustrates some important things about upper and lower sums. Notice for any value of n, the lower sum is less than or equal to the upper sum. Yeah, we were expecting that. And as you take the limit as n is approaching infinity of either little s sub n or the limit as n is approaching infinity of capital S sub n, you're going to wind up with the same answer, 8/3. Okay? You wind up with the same answer. Because as n gets closer and closer, bigger and bigger and bigger, these have lesser and lesser influences. These do. So you go to the same limit. So it doesn't matter which minimum, maximum, left hand, right hand, it doesn't matter how you split these up. As n is going to infinity, they get to the same result. The limit is 8/3 in this problem. Not in every problem. Okay. Now, I so much want to... Okay. I'll hold this off for a moment. And let's see how they did it. All right, to erase this mess? Yeah, I can see y'all are really excited for me to erase that. Okay, so how did they do? To begin with, partition the interval into n subintervals, and that's what we have. Delta x is equal to b minus a over n, which is 2 minus 0 over n, which is 2 over n. Good. We're right on the same page here. That's the width of your subinterval. Okay? Your inscribed rectangles are going to be the ones using the left-hand n, so that's going to be the n minus 1, because if you have n going from 1, 2, 3, 4, why did they choose 5 again? I don't know, but they did. They must have liked 5. They did it that way. The circumscribed rectangles, you're using the right-hand endpoint, n equal 1, 2, 3, 4, 5. Others you're using 0, 1, 2, 3, and 4. Okay? That's the difference here. Okay? So there's your inscribed and circumscribed rectangles when n happen to be 5. Doesn't matter what it is. Okay. So your left-hand endpoints will then be, the m sub I will be 0 plus whatever your I is, but you subtract 1 from it, so you get the left-hand endpoint, I minus 1 times your delta x. Remember, you start at 0 and do one interval over, that's 1 delta x. 2, that would be I minus, yeah, so you keep going over the counter, but the counter is subtracting 1. So that gave you your 2 times I minus 1 over n. Right-hand endpoints is just the, not I minus 1, but I, because you're using the right-hand endpoint, that would be 2i over n. A lot easier number to work with, okay? That's your m sub I. That's what you plug into your function. Whoa, they skipped a bunch of steps here. It's f sub n sub I, which is this thing squared. Okay? F of this thing, and when you do it, I jumped ahead. Delta x is the 2 over n. So it looks like you've done it twice, but this one's because that's what you're adding each time. This is the width. Height times width, that's the area of the rectangle. Okay, but your f is your squaring function, so you square the x, okay, and multiply by that. And that's where you came up with the weird I, and that's what you get. Summation I equal 1 to n. This is this lower one now. 8 over n cubed times that polynomial in I. The 8 over n cubed can come outside of the summation. Why they leave it in there, I'm not sure. Those are constants. You can bring them out. Okay? Oh, and they did. They finally did. And then they split this up as the summation of I squared minus 2 times the summation of I. plus the summation of 1. N times, that's just going to be n. So this becomes 8 over n cubed times this was this one, 2 times this is that one, and this is just n. And then I noted each of those has a factor of n, bring it out, make that an n squared. They don't do that until later, okay? They keep it that way. And they skip a bunch of steps just to make it fun, okay? The steps they skip is make this, multiply this by 3's here, okay? And multiply this by 6. So you get this 3 over 3, 6 over 6. So everything's over 6. And when you do all that, multiply through, do everything they want you to do here, this is what you come up with. They are skipping steps like crazy. They didn't show you how they multiplied that or that or that. But if you factor out the n, it makes it easier, but you still have to multiply. Anyway, that's what you get. Take their word for it. Okay? And then they go straight to this step. Here the n cubes go out, and that gives you 8/3. Here, 2 n's go out, that gives you just, and the 3's go out, so it gives you 4 minus 4 over n, and this one just gives you 1 n goes out, and 4 over 3 n squared. Okay? That's your lower sum. No matter what your n is, they chose 5, we could choose 4 million. Whatever it happens to be, that's what your summation comes up to. And of course, the larger the n, the closer that is going closer and closer to 8/3. Okay? Coming up to 8/3. Okay? Doing that for the other side, it's so similar. The good news is you only have an I squared. You don't have the i's and the 1's there. So you just have that one sum. And that one, when you do it, again, what I would do is like that, 4/3, okay, and just get rid of one of those and make that n squared. Then multiply your binomial, and you get that, 2n cubed plus 3n squared plus n for, oh, no, they kept the n in it. Now they're going to take it out, yeah, so to speak. And the n cubes go out here, and that gives you 8/3, same as you had before. This will be, the 3's go out, and n squareds go out, and that gives you 4 over n, with a plus here, and then 4 over 3 n squared. Okay. With the key being, the larger the n, the more these get insignificant, and your limit is 8/3. But that's coming to it from above, okay, because of that plus 4 over n. So here's the next theorem. Theorem 4.3 shows that the equivalence of the limits as n approaches infinity of the upper and lower sums is not mere coincidence. It's true for all functions that are continuous and non-negative on the closed interval a to b. Remember, those were the requirements. Continuous functions, non-negative functions, okay, have to be those things, okay. If f is continuous and non-negative on some interval a to b, the limits as n approaches infinity of both the upper and lower sums, or you could have done left sums and right sums, it doesn't matter. They both exist and they're equal to each other. Because as n is getting closer to infinity, guess what? The interval is getting smaller and smaller and smaller. Left and right, min and max, they're getting closer and closer to the same thing. So it can't avoid being the same, okay? As long as they're continuous non-negative functions, okay? So the limit of the lower sum and the upper sums are going to be the same. For delta x is b minus a over n. And those are the minimum and maximum values on the subintervals. It will work out that way every time. So why did we go through all that? Why didn't we just jump to this? In theorem 4.3, the same limit is attained for both the minimum value, the f sub little m sub I, and the maximum value f sub capital M sub I. So it follows from the squeeze theorem, oh, that was fun, wasn't it, that the choice of x in the ith interval does not affect the limit, okay? You could have used left and right hand ends. That's what most other books do. max and min. That's fine too. Doesn't matter as you get your intervals smaller and smaller and smaller, as long as they're continuous functions, those things are getting closer and closer to each other, so it comes out the same. So here's the squares theorem mentioned again, way back from chapter 1. If h of x is always less than or equal to f of x, which is also always less than or equal to g of x, for all x's on the open interval, okay, containing c, except possibly at c itself, then the limit of h of x is equal, and the limit of h of x is L, and the limit of g of x is L, then it means f of x has to have that same limit. So if the minimum sum comes out to the same as the maximum sum, and you know the f is in between, it's got to have that same limit. Groundbreaking, isn't it? Okay. This means that you're free to choose an arbitrary x value on the ith subinterval as shown in the definition of area of a region of the plane, and it doesn't matter which one you choose. Left hand, right hand, max, min, just anything in between. The average one, why not that one? Let f be continuous and non-negative on the interval a to b, the area of a region bounded by the graph f of x, graph of f, as long as it's non-negative, that's going to be something above the x-axis. The x-axis is going to be below it, okay? And the vertical lines x equal a and x equal b. That area is going to be the limit as n approaches infinity of the summation I to n of f of pick any value in that interval you want to. It doesn't matter which, delta x, as long as the c sub I is in between x sub I minus 1 and x sub I. Anywhere. It could be either one of those, the left hand, the right hand, or any one in between. The delta x is b over n. So, all right. Choose any c you want to. The middle c, the max c, the min c, the left c, the right c, it doesn't matter. Pick a c, any c in the interval, it'll work. Okay? Now, no, this is example 5 then. All right. Find the area of the region bounded by the graph of f of x equal x cubed, the x-axis and the vertical lines x equals 0 to x equal 1. Okay? Now this looks a lot like the last one, except that was a parabola. This is a cubic, so it's a little flatter here. It's steeper. It's beginning to be steeper as you go out there. Okay? Okay. They picked okay, they just give you the answer right here. They weren't supposed to do that, but they did. Okay. Your delta x, like we did before, start there. Delta x is equal to b minus a, 1 minus 0, 1 over n. There's your delta x. They kept this one fairly simple. Okay? Any c you want to choose there, just as long as it's in that interval, its value, let's call it c sub I, is going to be 0 plus I delta x. Okay, so this is going to be I delta x. Okay, delta x. Okay, pretty straightforward. That's going to be the value, whatever you choose to see. I guess you need a c sub 0 to begin with, but I don't think it really matters. So it's ugly. Your f at c sub I is then going to be I cubed delta x cubed. Okay? Oh, wait. Sorry. all that was correct, but we don't need to keep the delta x. We know what delta x is, 1 over n. So this is I times 1 over n. So this is going to be I over n. Okay? Now, that's your C sub I. Your f of C sub I is going to be I over n cubed. Okay? Multiply that by f of C sub I times delta x is going to be I over n, I cubed over n cubed times 1 over n. Okay? So that's going to be I cubed over n to the 4th. Okay. Now, what is your I cubed? Let's pull out the 1 over n to the 4th. Keep that on the outside. I have to go back and look. N squared times n plus 1 squared over 4. The summation of that would be n squared times n plus 1 squared over 4. I'll look and then I forget immediately. N squared times n plus 1 squared over 4. All right, going to have to do a little work here. Sorry. 1 over n to the 4th. N squared times n squared plus 2n plus 1 over 4. And this is n to the 4th plus 2n cubed plus 1, no, plus n squared over 4 times 1 over n to the 4th. Well, guess what? Those go out, well, let's write it down. That would be 1/4 times, no, this thing is irritating. Ah, finally it hit. Okay. It won't get, it finally gave me my pen back. Okay. Okay. It's 1/4 when n fourth over n fourth is 1 times 1/4 plus 1 over 2n plus 1 over 4n squared. That's what it turns out being. Okay? As n goes greater and greater, closer to 0, n gets toward infinity, those get closer and closer to 0, so the sum is 1/4. That's why they jump to that conclusion there. Okay? That is 1/4. I'm so wanting to show you the easier way to get there, but let's not yet. Okay? Begin by noting that f is continuous and non-negative. Yes, the cubic function is. On the interval 0 to 1. Next, partition the interval 0 to 1 into n subintervals, each of which delta x is 1 over n. I, again, forgot to bring up my watch, so y'all will let me know, right? How are we doing?
15.
11 what?
15.
15. Okay, we got plenty of time. Okay. So it's 1 over n. That's your delta x. Okay. According to the definition of area, you can choose any x value on the ith subinterval. For this example, let's choose the right endpoints where c sub I is equal to I over n. Okay? That's basically what I did, but I just said choose that. Okay, I over n. That's the easy one to choose. Okay? So your f of c sub I would then be 1 over n cubed. So that would be, this goes to f of this is 1 over n cubed, and your delta x is 1 over n. So basically you've got I cubed over n to the 4th. N to the 4th can come on the outside. There it goes. Well, no, not quite. You could bring it on outside the Nah, maybe not. Yeah, leave it inside the limit, but outside the summation. And that becomes your n squared times n plus 1 squared over 4. Okay? And they don't show you how they got it, but they did the same thing we did. Square the binomial, multiply it by n squared, and you'll come up with this. And that's the same thing we got. And as n goes to infinity, that goes to 1/4. So that's the area under there. The area of the region is 1/4. As n gets larger and larger, your interval gets smaller and smaller, and therefore you're approaching 1/4. In general, a good value to choose is the midpoint of the interval, which is this mess, okay? X sub I minus 1 plus X sub I divided by 2. That's the average between the two, okay? And they apply the midpoint rule, and then you'd be doing F of that thing. Does any of you really want to put that in for every X? Okay, I don't particularly. I just soon use X of I, the right hand, okay? That would be so much easier to do, but if you did this one, the midpoint rule, whoa, you are at the end of the section, okay? So that sounds good to me. They're skipping example 6, 7, and 8. 6 and 7 were just like the previous one. 8 is when they introduced the midpoint rule. So let's go back. Here is a good place to do 6. Now, they don't show it in the slide set, but they do show it at larsoncalculus.com. You can do an interactive version of this very type of example. Find the area of the region bounded by the graph of f of x is equal to 4 minus x squared, the x-axis, vertical lines x equal 1 and x equal 2. Okay? Shown in the figure. Okay? I'll just briefly show you what that looks like. Starts at 4 up here and goes down to here. There's 1, there's 2, and you're this area here. So we're going to do our increments here. There's going to be our rectangle, representative rectangle. Okay. All right. Your x sub I is going to be 1 plus. Notice we're not starting at 0, we're starting at 1 now. The A, 1 plus your delta x. But the delta, oh, well, we didn't do that. Okay, what's your delta x? Delta x is 2 minus 1 over n. That's the number of intervals, okay, which is 1 over n. Nicely done, okay? So that would be 1 plus 1 over n. Okay, that's your delta x. Okay. Your f of x sub I would then be 4 minus 1 plus 1 over n squared. Now, frankly, I find that a little awkward, so let me write this as n plus 1 over n. That's the same thing, isn't it? 1 plus 1 over n is the same as n plus 1 over n, right? Because n over n is 1. I think that's a little easier to work with, so let's do that. 4 minus n plus 1 over n squared. Okay, let's go on and work that out. 4 minus n squared plus 2n plus 1 over n squared, which will be, make this over n squared 2, So that will be 3n squared minus 2n minus 1 over n squared. Did you follow that? I know it's awkward and miserable and stuff like this, but your function is that. Your x sub n, x sub I is that, okay? So you're going to do 4 minus that squared, okay? And this thing squared over that squared, that's what that becomes. But get it all over the same denominator, make this 4n squared. So it's 4n squared minus n squared would be 3n squared, then minus 2n minus 1 all over n squared. I think I did it right. I hope so anyway. Okay? That's your f of x sub I. What you're doing, your summation, is that times your delta x, which is 1 over n. Yeah, there it is. 1 over n. That's your delta x. That's what you're summing. Okay. Oh, man. I'm sorry. I've been putting n's where I meant to put i's. Let me go back. This is so miserable. Okay. All right, I need an I in there, not a number. Let me make sure I'm getting it. It's 1 plus I over n. That's where I messed up. Well, sorry about this. Wait. Nah. Yeah. I thought I had my eraser on. Okay. Let's do this. Let's do this. Do that. And we'll come back and redo all that. Sorry about this. My ones and my I's look so much alike. I thought I was doing I's and I was doing 1. Sorry. Okay. X of I is that. Okay. Plus I over n. Because it's, you go the ith interval and that's how many you do. I times 1 over n is I over n. So this is an I over n. So this is an I over n. And this will be, now this is where I think it starts falling apart. Okay, sorry about that. All right, let's do that then. This will be 4 minus this will be n plus I over n squared. Okay, when you do that, you get 4 minus n squared minus plus 2 in plus I squared over n. And now and that will be over n squared. Sorry. So that'll be 4n squared minus n squared minus 2in plus I minus I squared over n squared. Okay. Okay. So that would be 3n squared minus 2in minus I squared over n squared. That's your f sub I. I sure hope I got it right this time. Basically looks the same. Okay? Now, we take that and multiply it by your delta x, which is 1 over n. Okay. Okay. Now, they do it differently than the way I'm doing it, but I think it will come out the same. I just don't have enough room to write it. Okay. All right, this is the thing we're going to be summing from I equal 1 to n. Okay, that is the product of those things. We can pull, the way I've done it, pull the 1 over n cubed out front. I'm hoping this is going to work because I'm not doing it quite the same way they are. And that will leave us with 3 probably not a good idea to have the n squared there, but let's see if it works. 3n squared minus 2I over n minus I squared over n squared. Okay. I kind of like their idea of taking that just 1 over n out rather than the whole thing. So let's do that. We'll forget about this one and leave this as a, yeah. That'll be an n squared there and the n cubed there. Okay, believe that'll work. I just don't have enough room to do. All right. What I think I'll do is erase, just so I have more room to write. My cord has gotten all twisted up here. Picking up from this, well, let me try it at the top. I don't know if it's going to be good enough to do there. Okay. Where we left off, I hadn't written down the limit yet, so let me do that. We're doing the limit, though, n equal, as n is going to infinity, of this summation. Now, they pull the 1 over n out. That has to still be there. Okay? Okay, now the summation that we have left, I'm going to try to do it in here, is just 3. This is I equal 1 to n. 3 minus 2I over n squared, I believe it is. No, over n. Because I pulled out the n, sorry. This is n squared. Okay. Okay. Minus I squared over n cubed. No. I pulled them out and then put them back in up here, sorry. This is n, that's n squared. Okay. All right. Now, that's sort of messy, so let's split them up separately. the limit as n approaches infinity, which is going to all go away anyway, 1 over n, and let's do the summation of I equal 1 to infinity of 3 minus 2 over n times the summation. I'm going to leave off all those limits, but you know what they're, the same thing. I minus 1 over n squared, the sum of I squared. Okay. Now I'm going to erase the stuff we have down here. At least this stuff. Okay. Because this is just using this that we wound up with here. And we go and look in our theorem and see what these values are again. And I think we're fairly clear on what most of them are. Okay. This will be, God, this is hard to read my writing here. The limit as n approaches infinity of, the first one is 1 over n times n. 3, sum 3 from 1 to n. Oh, goodness gracious. I can't believe I did that. N going from 1 to infinity, this is your n, not infinity. Okay. Sorry. Old gray cells are not working well today. Okay. Okay. Now, that just goes to 3n. 3 times n. 3 plus 3 plus 3 plus 3 plus 3 plus 3. N times is 3 times n. So that goes out. Okay. Minus 2 over n. Summation of I, remember that one was n times n plus 1 over 2. N times n plus 1 over 2. Well, the 2's go out and the n's go out. So that leaves you an n plus 1. Okay? Minus 1 over n squared. And the summation of I squared is n times n plus 1 times 2n plus 1 over 6. N times n plus 1 times 2n plus 1 over 6. Okay? Sure I wrote it right? Yeah. Okay. Now, going to have a little bit of work there to do. Okay. Something's wrong with that one, I think. Now I realize what I've done. I changed the wrong thing up here. This was 2 and this was 3. Sorry about that. This was 2 and that was 3. I had it right before and then I went back and changed it. So this is squared and that's cubed. Sorry about that. No, put the cube in the wrong. No, yeah. Okay, I think I've got it right now. Okay, so this sums up being 3 minus, and one of the n's goes out. Okay, and you're left with n plus 1 over n. That's 1 plus 1 over n. So that's just going to be a minus 1. Minus 1 over n. We'll put that one in if you want to. Okay, this one, when you multiply those through, well, I should have left this one before. It's 2n squared plus 3n plus 1. And multiply that by n, and you have 2n cubed, okay, minus, and this is all over 6, 2n cubed over 6, which is n, and you have an n cubed out here, so it's 1/3 just at minus 1/3, because the n cubes cancel out. And then you have, the next one's going to be a minus 1/2n and then the next one's going to be a minus 1/6n squared. Okay. But as n goes to infinity, all those go to 0, and you're left with 2 minus 1/3, which is 6/3 minus 1/3 is 5/3, I hope. Yeah, that's what they got. This is so tedious and so awkward to go through all this, but this is what you're doing if you're actually using the limits, okay? And you just have to bite the tongue and go, okay? Proceed with it. Now we're supposed to do example 7. Do we have time for 7?
3 minutes.
3 minutes. I kind of doubt it, okay? So let's end here. Okay, and we'll pick up with example 7 next time. We almost finished 4.2. We will finish it next time. Okay? Homework exercises would include any of the odds 5 through 9. They're all at Calc Chat, 5's at Calc View. Any of the odds 11 through 15, they're all at Calc Chat. 17 to 23, they're all at Calc Chat. 21's at Calc View. Either 25 or 27, they're both at Calc Chat. 25's at Calc View. Any of the odds 29 to 33, they're all at Calc Chat. 33's at Calc View. Do 35, it's at Calc Chat. Do either 37 or 39, they're both at Calc Chat. 39's at Calc View. Either 41 or 43, they're both at Calc Chat. 43's at Calc View. Take a look at 45. I think you can do that one. And then any of the odds 47 to 55, they're all at Calc Chat. 49's at Calc View. And then this is on page 288. Then any of the odds 57 to 61, they're all at Calc Chat. 57's at Calc View. Hold off on the midpoint rule. We'll do that one next time. So stop at 61. All right, get out there and enjoy L Day. There should be some free food involved. That's always appropriate for students. And remember that for those who came in later, next Wednesday we do not have class. They're making all of us full-time instructors go to Montgomery for a meeting with the chancellor's staff. So we will not have class. That doesn't mean you won't have any classes. Check with any other instructors on Wednesday. If you have an adjunct instructor, that class will probably still continue. All right. Good deal.
By Tuesday, could I see a solution to the last test on?
I'm sorry?
By Tuesday
Yeah.
of next week, can I see a solution on problem number 2 of test 3? There was one other one.
Okay. Okay.
If I had the thing here.
Okay. I'll try to, test 3, question 2, and one more. You said? Huh?
It may have been 5.
5, okay. I'll look at yours and see if I can guess which one you're talking about.
Okay.
Okay. And I'll try to have that.
I
can't
pick it up on Cal Chat somewhere.
Right.
But I just started guessing at it, and
Okay.
I screwed it up. I know I screwed it up 2 somehow.
Okay. I will try to take a look at that now. I'm not going to have any time until Friday, and if I can just remember to Friday, I'll try to work those. I'll try to take your test with me when I go to the Birmingham campus on Friday and get those 2 done. I can't talk about them on this because others haven't turned them in, but I'll just have it worked out.
That's what I was waiting until.
Right. Okay.
Okay, thank you.
All right.